So it's really nice to be here. It has been a while since I've given a lecture, since I moved to NVIDIA 2 years ago, but I hope I haven't lost my touch. So yeah, today I was thinking like what to present, because this is in the end a robotics seminar and I'm not a roboticist, so we are working in perception mostly. So I was thinking about bringing a little bit of the work that we're doing in segmentation and tracking, and especially focusing in the work that we're doing in 3D. Right? So there's two key words in the title that I want to highlight. One is the fact that we are going to be working in an open world vocabulary fashion. So we don't want to be, segmenting and tracking cars or people. We want to really literally find any object that we can find in the scene. And we want to do this in 3D. So let's see how we would go about this. Well, first of all, why do we need this, right? I mean, I think I don't need to explain to anyone how embodied autonomous agents work. But some of the work that we're doing in my group is around these three pillars, which are key towards enabling autonomous agents. One is perception, to understand what is around the robot. The second one, and perhaps this is the most important one, is how do objects move around the robot? And again, here, not focusing only on, cars and pedestrians for autonomous scene, but any object that can move in the scene. And the third one is essentially localization, right? So you want to be able to localize yourself, even in scenarios where you have a lot of repetitive structures, where you have very similar features all around. And this is kind of also something that we're working on. Now, for the purpose of this talk, I will focus more on the perception side and on the tracking side, and I will not talk about the localization work, but I'm happy also to discuss this after the talk. Okay, so if I had to summarize this talk and let's say the work that we're doing in my group with one sentence, it would be dynamic scene understanding. So we want to understand the scene around us, and we want to pay special attention into how objects are moving. Now, if we would go about this in a classic machine learning way, right? We would say, well, on the one hand, we have several tasks, and I'm going to frame the task from easy at the bottom to more complex at the top. And then we have on the x-axis the number of classes, right? So we can start with a few classes, which I will put on the left, all the way to open world, which is where we want to go. So let's start with, one basic task, semantic segmentation, right? So this is the task of actually assigning a semantic class to each pixel. And we can do this in a, supervised way with for a handful of classes. So there's tons of data sets out there with, people, trees, cars, road, like all these elements that are crucial for autonomous driving. We have good data sets for those, right? And we can train a model in a supervised fashion. It works pretty well. That I would say is not really a problem that we need to solve nowadays. We can even scale up to thousands of classes if you want. So there's the Elvis data set, tons of data sets that are focusing on, expanding this vocabulary. And you can still do this in a supervised fashion. Let's start looking at the task axis. So if we want to increase a little bit the complexity, if we want to have a deeper understanding of the scene, we need to have not only semantic segmentation, but we actually need to go towards panoptic segmentation. And for this, I actually mean not only saying, hey, all these red pixels belong to the class person, but actually identify the different people in the scene. And again, for a handful or not thousands, but maybe hundreds of classes, there's data sets for that. Let's just now add the temporal domain, right? Now you want to basically segment and add a semantic label to each of the pixels. You want to identify instances, and you want to track those instances in time, which means that you want to have the same ID for all the frames where you're actually observing that object. And I would argue that tracking is easy if the object is nice and visible. It starts to be complicated in crowded scenes, for example, when objects interact with each other. There's lots of occlusions, there's lots of similar appearances. This is where things get really interesting. Now, for a handful of objects, like especially pedestrians and cars, there's tons of data sets. It's doable to train a model in a supervised fashion. It works relatively well. I think this is a problem that we know how to handle. When we talk about 1,000 of classes, this is a different story. But where we really want to get to is lifting again to another dimension, and this is the 3D dimension. And this is where there's, not many works that are working in this domain, right? So a lot of works that do tracking or segmentation stay in the 2D domain. But if we really want our autonomous agents to understand the surroundings, these are in 3D, right? And I would even argue that we have 4D because we have the temporal domain. So essentially what you want is you want to have 4D dynamics in understanding. Now what happens is that the data sets for this kind of data, here I'm just showing like some preliminary results that we had with our method, and these are projected onto a LiDAR point cloud. So what we're seeing here is a car driving around and it's sensing different instances of different objects. We have like traffic lights, we have the streetcar, we have the road, and these all need to be segmented, these all need to be tracked. Now, ideally, what we would want is we would move to the extreme of this axis, right? We would like to have 4D panoptic segmentation, and we would like to have this in the open world. So you can imagine that doing this in a supervised way is completely not feasible. So again, for semantic and panoptic segmentation, how the community went about it is, until 1,000 classes, let's get some data. For semantic segmentation, it's possible. For panoptic, hundreds of classes, it's still possible. For tracking, we did pretty much the same. Let's get some more data. So I know quite a lot about this because my postdoc was spent annotating bounding boxes for Mod Challenge. So this was fun. One thing about annotating videos is that it's very repetitive. And what I mean is that, for example, tracking one person, right, means annotating the same person for 1,000 frames, right? The appearance of this object is the same for 1,000 frames, which means that the variability that you get when annotating these 1,000 frames in the appearance axis is basically nothing, right? So if you want to get varied appearance and you want to get varied motions, like it quickly explodes how much data you have to annotate. So annotating videos is really not the same as annotating images. So this was basically my postdoc. We had to annotate, 100 similar frames. We had some techniques to actually alleviate a little bit the pain. And I'm also happy to discuss this offline, but I think it was still like quite a lot of manual work for the amount of benefit that we got from the data. But, if the real world is going to be in 4D and it's going to be open world, it starts to be, hard to think that we can actually collect this amount of data. Like, there is just no way. So what I'm going to propose to do and what I'm going to present in this work is a couple of works that say, well, let's not really throw away all the data that we have already annotated, right? Let's actually use it. And let's try to create some sort of pseudo-labels for our problem, which is in 4D and which is open world. So I'm going to focus on creating 3D and in particular LiDAR pseudo-labels, and I'm going to present two methods. The first one is looking at the appearance of the objects. The second one is looking at the motion, and they serve two purposes, as I will explain. So looking at appearance, I'm going to present our work, Segment Anything in LiDAR, which is going to be about localizing objects in 3D, assigning a semantic meaning to them. And the main takeaway there is going to be how to leverage vision foundation models. When we're looking at the motion, what we're going to want to do is forget about the semantics and just say, let's try to find points that move together. And let's try to cluster objects based on motion, right? Kind of like the classic motion clustering, very similar idea, but in a learned fashion. So let's start with the first one. So this is a little bit of a video demo that we have, and I actually have an interactive demo later, so you can, you'll be able to give me any prompt that you want to break the system. But in here, what I'm showing is in blue, the trash cans, and in yellow, the fire hydrants. So the question is like, how many fire hydrants and trash cans are you going to see in your training data? Just a handful, right? So it's impossible to train a supervised method that works with this accuracy. For example, for these objects of trash cans and fire hydrants. I think we saw like 2 fire hydrants in the whole data set, and we're still able to capture them in the validation sequences. So how does this model work? So it's sort of a way, let's say 2 words, a LiDAR foundation model. I would still not call it a LiDAR foundation model, but let's say laying the groundwork for that. And the idea is that you want to take your LiDAR point cloud and you want to take your text prompts, right? What do you want to detect from the scene? The, fire hydrants, trash cans, or even common objects like cars or persons. You want to pass them onto our SAL model, and this will give you instances plus semantics. So basically, you want to segment and classify any object. And again, here we're talking about panoptic segmentation, right? Like the instance part is very important. Now, again, we could go about this by manually annotating large-scale data in 3D. This is absolutely painful. I think inside NVIDIA, we have like a few annotated sequences, and this was complete painful to obtain. So this is really not scalable. So what we said is, okay, let's try to benefit from existing 2D annotations, from existing 2D models, and let's see how we can bring them to 3D. So SAL is maybe like 2 concepts, I would say. So SAL is a pseudo-label engine, and it's also a model. So at train time, we're going to have unlabeled camera and LiDAR data, which is nice and calibrated. This is going to be passed onto a pseudo-label engine, and this is going to work with 2 foundation models. It's going to work with SAM, which is going to give you the segmentations, and it's going to work with CLIP, which is going to give you the semantics. Now, again, these foundation models, they don't work in 3D, right? There's some 3D clips and so on, but these are 2D vision foundation models. And the question is, how do I distill this information and create pseudo-labels so that then I can train a SAL model? So the pseudo-label engine is going to transfer these 2D vision foundation model information to 3D labels. And then the SAL model is going to be able to perform zero-shot segmentation via text prompting. And this zero-shot segmentation is only going to happen in the LiDAR domain. So at test time, we don't really need the images. Okay, so let me just briefly talk about the SAL model. It's really nothing fancy, right? So it's going to take our LiDAR point cloud and our text prompts. As a model, we're going to have class-agnostic segmentation in a mask-to-former kind of way, in which you have, your backbone, you process your LiDAR point cloud, and you have your transformer decoder, which takes a set of object queries and decodes them into the actual instances. So you're going to have the mask, and you're going to have an objectness value. So the architecture is pretty simple. There's nothing fancy about that. What we're going to add in order to make our model promptable is we're going to predict also from our object queries a clip token. And this clip token is going to be aligned with the embedding that we will obtain from the actual text prompts, right? So here basically how I'm training this is I say, if I segment a mask of a car, I want the clip token to be very aligned to the embedding that I obtain with clip from the actual word car. So this is a way to sort of bring clip to 3D, right? Because now what I'm doing is I'm pairing 3D masks with my clip token. And with this, I can then do zero-shot classification, right? So imagine at test time, I type the word car, I obtain my clip embedding, and I look at all the masks that align well with that clip embedding. Now the question is, okay, how do you actually train this model, right? Like how do you actually obtain labels to train this model? This is a fully supervised model, right? I mean, we do need some labels to train that. Now, this is where the pseudo-label engine comes in. So here you see the input that we have. At train time, we do need images, right? We do need to distill this 2D information coming from foundation models. So we have these kind of images that are looking around the LiDAR point cloud. we also have the LiDAR data. They do need to be calibrated, because what we're going to do is we're going to apply SEM onto our image, and then we're going to unproject the information into 3D, right? So this is why I say that calibration is important. I think public data sets are relatively well calibrated, but if you've ever worked with LiDAR and cameras, they don't have the same viewpoint. So usually the LiDAR is a little bit higher up. It can look behind an object, which the image doesn't see, and this creates tons of problems in 3D. So what we have then is also we pass the masks in 2D through clip to obtain the embeddings, right? This is just classic mask clip. There's also nothing fancy there. So now what we have implicitly is we have correspondences between 3D masks, because the 2D masks have been unprojected to 3D. We know the ID, and we know what is their corresponding clip embedding. So this is all the data that we need to train our model in a supervised fashion. Now, the pseudo-label engine is not just unprojections. So as I said, there's tons of problems when you just naively unproject, like there's tons of bleeding effects. Usually, like, you know, since the LiDAR, as I said, is a little bit higher up, you get all these points that are suddenly, you know, for example, the car points are suddenly passed through, you know, a line in the background, which is, you know, goes up to whatever, 10 meters or whatever that is in, you know, your units of measurements. So it's really a mess. If you look at that, projection is really a mess. So what we have to do is we have to sort of combine the notion of segmentations that we gathered from 2D with 3D clusters, right? By looking at the actual point cloud, by looking at the actual 3D clusters. So what we do is we apply dbScan, like super standard technique for point clustering based on, you know, relative distances. You can put tons of information in there. You could even have a learned version for dbScan. But I guess the idea is that we want to clean a little bit these effects, these bleeding effects, by saying, look, it makes no sense that there's a car point 10 meters away from the car onto a flat surface, which is potentially a building. So this is what dbScan can nicely do. So here you can see like some of the results of this, of the effect of dbScan, right? Like, for example, the bushes are nicely segmented. The car has less noise. The car in the background also has, you know, less noise. So I think overall, this is an important step. And, you know, many of the papers that are actually working in 3D, mostly indoor scenes that use this idea of, you know, distilling 2D vision, foundation models information, projecting them onto 3D, they usually stop here. They usually say, you know, now I have my information in 3D, that's all I need, right? What we actually found is that actually training the model on top improves things quite a lot. And so here I'm just like plotting a little bit of the results. Like in the first 2 rows, I'm going to have just the unprojected SAM masks. In the next 2 rows, when you see like SAM plus DBS, this is, you know, the dbScan, which improves things, right? If we're talking about the first column of results, PQ, which is, you know, the standard segmentation metric, you're going to go more or less from, you know, 42 to 48. But here's the interesting thing, right? When I actually train the model on these pseudo labels, suddenly my PQ goes up to 70. And I think this is the key learning here, right? These are completely free pseudo labels, right? But they are very noisy. The thing is that if I'm looking at a lot of data, so I have a lot of pseudo labels and they are noisy, and I train a model on top, the model kind of learns to collect the signal, the good signal, from this noisy data, right? There is no way that I could get to a 70 accuracy just with pseudo labels. But the model is able to distill this data from the free pseudo labels that I have just obtained. So I think this is like one crucial contribution of our work, was to say, let's actually train a model on top of these labels. Let's not just use them as predictions, but these have to be pseudo labels. Another thing that I wanted to focus on is the evaluation between segmentation and semantics, right? So here's something that we found very interesting, actually. And that is that if we actually evaluate only for class-agnostic segmentation, meaning that I have a semantic oracle, right? So I forget about the clip tokens, and whenever I have a mask, and, mask of a car, for example, I look at my ground truth and I take the actual ground truth semantics, right? So at the top, all of these results are without the clip tokens. And so you can see that when we actually have the clip tokens, which are these rows here, the accuracy suffers quite a lot. And this basically means that we can actually do segmentation pretty well in 3D, without any labels. When we're looking at semantics, we're really lacking behind a supervised model, right? Now, this finding is not really new. This finding is similar to what we have seen in 2D with 2D and supervised models. And I think this just means that we're going to have to take the localization aspect of SAL and really use it. But the whole semantic part is maybe something that we will do with another method, with some retrieval method, with, enhanced features and so on, because we're really not at the stage where we can actually use this by just using the clip features. So, okay, how does SAL work? So here I have a demo. This is still the video. So these are just instances. They're not connected in time. So these are just, single frame predictions. But we can already start seeing some interesting things, right? So for example, we have these traffic signs in blue. We have the street card, which is in brown. We also have the cars in brown. We have trees segmented separately from buildings. So you can see that SAL is really starting to understand quite a lot the context and really segmenting each of these objects separately. So, okay, before I go to 4D, I do want to do the live demo, which I hope it works. Okay, so let's see if I can select an interesting frame. Actually, I didn't prepare for this, so this is really, truly a demo. Okay, so here we can see the images. The images are just to show the results for better visualization. But remember that SAL is only acting on the LiDAR point cloud. So the input at test time is only the LiDAR point cloud. So let's see. We can start by detecting, for example, cars. This is kind of easy. So you put your prompt car and you obtain, the segmentation of all the cars. You see, there is still some bleeding in some of the predictions, but overall the localization is good. We can also do things like persons, for example. You detect some of the pedestrians in the scene. So here you can see it better in the image. We can do things like traffic lights. This becomes a little bit more interesting. Sometimes there's a confusion between traffic lights and traffic signs, like stop signs, for example. It tends to detect quite a lot the pole, because again, this is only using LiDAR information, right? So it basically understands geometry. So the pole of a traffic light or the pole of a traffic sign, that's pretty similar. But we can also do things like storefront, for example, which does detect, some of the stores. I mean, it's obviously similar to buildings, so there's not going to be this kind of semantic understanding just from the LiDAR points. Yeah?
More like construction work.
So we can detect that. Oh, now I don't know if we have. Let me try another frame. We can detect. Oh, wow, that didn't move quite a lot. Let me just go down. I don't know if this sequence has it, but I'm thinking no. No, I don't think it's this sequence. So things that I've seen working are construction barriers. This is detected perfectly. Traffic cones, for example. This is also good. What else? Yeah, construction-wise, that's. But these are well detected. Yeah.
Good question. Can you ask conditional queries? Can you ask about relationships between things in the scene?
No, not with this model. No. If you actually put, a car that is turning right, and this is not detected. For sure. So what we're thinking about and how this could be done is basically by having a dynamic scene graph, right? Where each object is actually not just, this point cloud, but you do have some interactions that then you can learn. And then I believe that this would be possible. To be honest, there's so much prompt engineering to, make very specific cases work that it's crazy. I mean, if I put car and then I put cars in plural, sometimes the result is different. So this is a bit painful, but I think that you can find nice recipes so that the result is consistent.
Right, the LLMs are kind of like a crappy API, right? They're like an API that's
it's very natural, but yeah, maybe very crappy, yeah. Yeah. I don't know if there was another question, or you can just ask for prompts. I mean, if there's any object that you see, because I really don't know these seeds by heart. Yeah?
You try fire hydrant?
Oh, yeah, that's you see the logo, our logo, right? Yeah, that's because we can do fire hydrants. But I'm not sure that there's one here. Let me try. Oh, yeah, there's one here. Oh my God, this is one here. There's also sometimes these kind of errors where you actually detect a road. So what we usually do for this is we do cross-check between queries. So for example, if there's sidewalk, I think sidewalk would actually fire there. But let me try. Yeah, sometimes the sidewalk is nicely segmented. Sometimes it segments the whole road. And then what we do is usually we cross-check things like, okay, road versus sidewalk. And then we do, intersection, union. And this works pretty well. Yeah?
How about debris?
Let's see if I write it correctly. Is this how it's written? Okay, good. I don't know what you're expecting to see in this scene.
Debris can be really specific. Debris could be anything.
In general, it's just if there's I don't know, a piece of a headlamp on the road, or a little animal. Will it actually, has it been treated to?
No. This is why this is going to be the motivation for the next work. So what we're trying to find is any obstacle in the scene, for example, this is not doable. You really have to specify, there's a salmon on the road, or there's a, whatever animal. I say salmon because I used to have this video to motivate why you want to have open world tracking, where in Seattle at some point there was some flooding and there were salmons on the road or something like that. So that's why I always think about salmon. I'm not that weird. But you have to be very specific about your queries. Yeah. Yeah.
Can you try tree or plant?
Yeah, sure. I don't know if there are any trees here though. Okay, not bad. I think the one on the, this one is probably better, but I don't think you can see it from the cameras. So one interesting thing maybe is that we cannot see some things from the cameras, but we still want them segmented. And depending on the data set, you don't have 360 coverage of the scene, right? So then what we do is we create what we call the Frankenfrustum for the Frankenstein, in which we basically overlap different point clouds without, there's no semantic relationship between them. We just want to have pseudo-labeled point clouds in a 360 fashion, and then we train our model with that. And then the model is able to predict 360 coverage. So this is why you're actually seeing this tree, but it's not really in the image. So maybe I can find a sequence with more trees. I used to have a better selected set of, diverse sequences. Oh, okay, so here's a night. So this is going to be interesting. Now I'm scared because I haven't tried this before, and if it doesn't work, then it looks really bad, right? Okay. That's decent. Good. I think we can call it a day. I'm happy. No, actually, if you want any other prompts, just let me know. I can also we can also play with this later. Yep.
What's the use of self-driving cars to be able to label objects on the side of the road?
So imagine that you want to do like full scene understanding, right? Like you really want your car to understand, you know, when there's an obstacle in the scene, where the sidewalks, if there's, you know, an object walking on the side and then about to cross, right? You want to be prepared for that. So I think the sides of the car are actually pretty important, right? Maybe less so for, I don't know, trees, unless there's a tree in the middle of the road, right? But like this tool is something that we envision more for labeling, right? Like this model is not going to go in the car, right? You're going to be prompting in the car. Like this makes no sense. So this is more for labeling, right? Like imagine that you want to find interesting data. You want to find data with a tree in the middle of the road, right? You can now prompt for this and say, okay, in your, 1 billion hours of self-driving, like where are the trees in the road? And then this is something that you can prompt. It requires a little bit of handwork because you need to establish the relationship between tree and road, which, as I said, is not automatic. So this needs to be rule-based. But this is something that you can do. And then you collect, for example, training data like this, right? Yeah. Yeah.
Well, when you say relationships, are you using like knowledge graphs to help design to connect those relationships?
I mean, so how I would do it from my professor head position is I would create a dynamic scene graph. I would learn this with graph neural networks. So it would be something learned. If you have to say, let's, give me a solution by tomorrow in a more practical way, then you can do this rule-based, right? Yeah. I mean, you have the 3D position, right? So you can really say, okay, if there's a tree that touches the road, right? And this is, for example, not the sidewalk or not something else, then you can say this is an interesting scenario, for example. Okay. Then I think I'll go back to the talk. Okay. So before I've said that we don't want to have these, single frame predictions, right? We actually want to go to 4D. And so here I have like some super preliminary results. And by preliminary, I mean that I got them this morning. These are still preliminary results, but basically what we're working on is on extending this understanding to 4D so that we can obtain temporally coherent instances, right? So that we can obtain tracks of the object. So that when I prompt for car, I actually obtain the track of the car and not just one instance of the car. How we're going about this is like very simply, right? Like we just say, okay, let's accumulate point clouds into one, let's say, single canonical frame. And let's do the pseudo labeling as we did. Of course, like it requires a bit of magic because there's the temporal domain, nothing agrees from different frames. And then let's train a model on top. And these are basically like some first results. Maybe I can find later the video and show you offline. But essentially, so essentially this was our work cell, right? So we found an easy and scalable way to get data. And instead of just saying, let's use this as predictions, we proposed to actually train the model. And we really found that this was a huge benefit. But there are still some instances, like the debris, right, that you're not going to be able to recognize with a specific prompt. And so we were asking ourselves, like, okay, is there anything that we can do, right? So far we have looked at the appearance, like that this is all based on appearance, like SAM is based on appearance, CLIP is based on appearance. But what about the motion, right? So dynamic objects are in general what you're interested in for autonomous agents. So how about focusing just on those? Can I detect any moving object even if I don't know what it is? So this is basically the second work that we call What Moves Together Belongs Together. And the idea here is let's try to find clusters of LiDAR point clouds that move together. And let's use those as object instances. And then we're going to, again, train a model on top. So let me go a little bit more in detail here. So we're going to do what we call motion-inspired pseudo-labeling, which is, it requires a little bit of labeled LiDAR streams. So we do need a little bit of LiDAR data annotated. But then the great benefit here is that we're going to use tons of unlabeled LiDAR data. And what we're going to do, or let's say our goal is going to be to train an object detector, a car detector, for example, that is just going to be trained on observed moving objects. So let's see how this works. So the object detector, it is nothing fancy. I'm not even going to talk about it. You take, your off-the-shelf object detector. What we're really interested in is how are we going to do the pseudo-label generation? And so here's the big picture. So we're going to have a little bit of pre-processing so that we have, for example, scene flow computed on the LiDAR point cloud. And so we're going to have some trajectories for LiDAR points. In general, these trajectories are quite short. And so what we're going to do next is we're going to cluster these trajectories. And we don't really want to do this in a heuristic way. Like, this is super complex because you're going to have, cars that are relatively big, then you're going to have people that are relatively small. So finding the hyperparameters, for example, in dbScan to cluster these trajectories would be completely insane. So what we propose is let's do this in a learned fashion. And finally, once you cluster trajectories, then you can actually find objects, right? Let's say I have, I don't know, like here I plot like 5 trajectories for the car. I cluster them. I say, hey, these belong together. This is an instance. Now I can suddenly place a bounding box on top of this car, and this is my detection. Okay, I will talk more about the GNN a little bit later. The object detector training, again, like there's no secret here. We're going to apply our method to unseen data. We're going to take these data as pseudo labels, and then we're going to train an off-the-shelf detector. So a little bit the same idea as before. So okay, what's happening with the clustering method? I think this is the special part, right? So we don't really want to do this manually. We have like some baselines on how to do this with dbScan in the paper. But I think here the interesting part is that you can actually learn to cluster using graph neural networks, right? So what we're going to do is we're going to create this graph where the nodes are point trajectories. So remember that we pre-process the LiDAR sequences, we obtain scene flow. So we do have some sort trajectories for the LiDAR points. And then the edges are going to connect trajectories that might belong together or not, right? So this connectivity says, these are all the possible connections between point trajectories. So now, to actually learn which of these connections is true and which of these is not true, we can use message passing, essentially, to learn this. So again, nothing secret here. So the idea of a message passing network is that you share features between nodes and edges, right? So the embeddings of the nodes and the embedding of the edges are passed along the graph. This is, of course, in a learn step. You have your MLP that collects the information. And so after all of these message passing steps, essentially what you have is a graph that has knowledge of the surroundings, right? So imagine one node, which is one trajectory, which has a good knowledge about all the other nodes in the surroundings, right? Because they have shared embeddings. So now suddenly it's easier for this node to say if it, belongs together with the other trajectories, because you have all this shared information now. So the only thing that you have to do in the end is you have to train this graph neural network for classification, right? You want to classify edges into active. An active edge means that 2 point trajectories belong to the same object. An inactive edge means that they don't. Then you do some cleaning with correlation clustering, and you can extract the bounding boxes. So I don't want to go too much into detail on results, but I do want to show a couple of numbers. So first of all, I want to show what is the gap between ground truth, so actually training with all the detection bounding boxes, and the pseudo-labeling method, right? So the same as for SAL, we're going to have a gap between ground truth and the trained model. And in this case, our gap in terms of precision is, between the purple line and the green line. So you can see that, it's not perfect, but I think the cool thing is that it's much, much better than the yellow line, which is actually trying to cluster these point trajectories with DB-scan, right? So I think that's a really important thing, because previously how people did it is by using DB-scan to cluster and to find these objects. And we have really a huge improvement there. So this tells me that this is, the right direction to continue. The other cool thing is that, as I said, DB-scan has all these parameters that you need to tune, and you even need to tune it per data set, right? Well, what we found was that we could transfer between, for example, GNN trained on Weibo, we could transfer to Argoverse very easily, and we could even detect new classes, right? So trained on cars, for example, and then we could detect buses. So I think this shows that the method is much more general than, for example, DB-scan. So these are some of the results that we have on Waymo, right? All these red bounding boxes are the ones that we detect as cars. And again, here, the goal is not to be perfect, right? I mean, these are pseudo labels. I'm going to train a model on top. This is basically free data. So I think maybe a message that these two works are sending out is that if you have tons of data, just pseudo-label it for free, right? Tons of it, really tons of data, and then train a model on top of this noisy data. And this gives you actually quite decent results, or at least a decent starting point. These are results on Argoverse. Again, we never see Argoverse during training. So you can see that some objects like big trucks or big buses, which are present here, sometimes they are difficult to cluster, but still it shows pretty good generalization. Okay, so I do want to leave some time for questions. So let's say if I had to distill all of this talk into, 3 take-home messages, one would be that pseudo-labeling is a super powerful tool. You should really leverage 2D foundation models, and you should not be retraining those for 3D tasks, right? The important thing is to distill the information from them. Don't go ahead and collect manual data to train a 3D clip, for example. I think there are geometric and 3D motion cues that still need to be explored, right? This is just kind of a first exploration of this, right? I mean, there's tons to do, and I think there's a lot of interesting things to do there. And there's a lot of good generalization to unseen classes, to open world vocabulary. And finally, what we actually want to do with these two works is sort of open up possibilities in 3D without require any labeled data in 3D. I think labeling data is painful. Labeling data in 3D is even more painful. So we should really be trying to avoid that. With that, I will conclude my talk. You have the link if you want to see some of the research that we're doing. And I will be happy to take any questions.
Recently, when SAM 2 came out, it seems like the sort of inter-frame mask tracking is pretty good. How do you think that's going to play through to some of your work? It seems like it would be a pretty useful feature to leverage.
Yeah, we tried. It's not good.
Really?
So let me tell you. So we're interested in long-term tracking, right? So we're interested in... So for me, let's say SAM 2 is more like a video object detector, right? In the sense that, as long as you see these glasses, SAM 2 can track can track them, can segment them, no problem. If I hide them, then, it's over for SAM2. If there are many similar objects, it gets quite confused, especially if there's a lot of occlusions. So for what, for the interesting cases of tracking are not solved by SAM2, right? Of course, we do leverage it. So the results that are presented for SAL in 4D, these are with SAM2 as a pseudo-labeling method and not SAM1, let's say. It does have a little bit worse semantic accuracy, but I think they now have released a version that is then better. So, this might be information of last week. But yeah, you can leverage it, but for short-term tracking, I would say. Yep.
How good are the sensors at telling the difference between let's say roadkill or a cat that's laying down in the middle of the road?
I would say really bad. But I also I don't know how interesting that is for a car. Because if the animal is dead, then you just don't care, and But yeah, I don't know. I don't do that, so I hope that no one does that and just runs over the animal. I think that it's
It's the movement part. Actually, the animal is moving, right, versus just being still.
Right. But what I imagine is that, or I'll say the difference that I imagine is that if the car is still but alive or dead, right? Was that a question? Yeah. No, this is hard. Yeah.
So that's something you guys would want to try to work on, or because
I don't think so. It's more about the obstacle being there, right? I think this is super fine-grained. I think autonomous driving is not far enough, that that this is your main problem, right? I think there's tons of other problems to solve. So yeah, I think it's more about the actual localization of something on the road and then giving it, a target, a tag, right? So if it's cat, if it's alive or dead, that's, I don't know, I don't see the impact there. But maybe I'm wrong. Maybe it's an interesting problem. Yeah.
if the cat would move or something, because I don't know, some cats are done.
I mean, if the cat moves, then sure, right? Then we can detect it with the second work. That's putting motion features together with appearance features. That's also something we're thinking about. This for sure. Yeah.
Because I would assume you wouldn't want the car to just if the cat was alive, they just go over it.
Yeah, I would argue that it should just go around it either way.
Okay.
Yeah. Yeah.
How does the underlying LiDAR hardware matter in the model? Because there's new types of LiDAR called frequency modulation, which can detect both velocity and position. And if you want to train a better model, utilizing that sort of information as well instead of just a mechanical scanning LiDAR.
Yeah. So I have to say, the method is it doesn't even transfer well across LiDARs, right? So if you try the different public data sets with different LiDARs, the point distribution is just different, right? You could actually train a model with any new type of information, even with radar information, right? And of course, it would help you in the case of 4D to have velocity information, right? That's clear. So radar can be interesting. I don't think you would even need to change the method. It's just a question of what's the input, what's the output. But I think the method could be the same. Yeah.
Can you explain the pseudo labeling again? So pseudo labeling is 2D, 3D only, or just 2D? Or doesn't matter?
So the pseudo labeling is the idea of taking automatic output of a model, right? Something that you haven't labeled manually, and transferring it to 3D, right? This is what we call the pseudo labeling engine. So basically, it's obtaining labels for free. That's the core idea. Yeah.
So it sounds like your job is sort of in the real-time perception stack. Is that right?
Real time, no. It's more for actual labeling. Yeah. I mean, this method is not real time, right?
Your models they'll be some of this will be on car. It will be none of these.
I think there's people that can optimize the methods at NVIDIA. These we know how to do, but that's not. It's not. I would not say is the goal, right? I think the goal is to have better understanding of the data that you have, and once you understand the data, then you can train a really fast model. Yeah.
I actually was going in a different direction. So
Okay.
one of the things I always thought would be really nice that NVIDIA could push toward is things that make, you're going and you're setting up a model for your robot in the lab or outside or whatever. It'd be nice if you could take some data and boom, you get something in OpenUSD or IsaacSim, just like that.
Yeah.
Okay? And I'm just wondering if like NVIDIA, there's interest or there's a name for closing that loop where things are actually in SIM, so that I have an IsaacSim model of something just by a robot view of it. I get things that predict, right? You're modeling the scene.
Yeah.
You're labeling objects. So just give me a 3D model of the whole scene.
There are some works in that direction. I would not say it's done. Yeah. But we do a lot of also reconstruction and adding semantic information into reconstructions, right? Like adding this information into Gaussian plots or nerves or something like that, right?
But they're still not a thing. They're still kind of an image. They're not a 3D model.
Right. But then you can convert this into simulation. I think these we're pretty good at doing. Yeah.
There must be a name for that sort of thing, right? At NVIDIA, you must
You
call
mean a
that
product?
something. There must be a name for that sort of process because it could be used for people that are using OpenUSD to create things. Creators could use it. It seems it would be a large.
Yeah, could be. I'm not super familiar with that part of the company, I have to admit. But I can see the connections. Yeah, definitely. Yeah?
About prediction tasks, so it seems like what you presented in the 4D panoptic segmentation, there are kind of two avenues in which you can do prediction. One is the LiDAR is probably incomplete. So like if there's occlusion in the back of a car, how do you know how far the back of the car extends? Can you predict, basically in-paint the rest of the car in 3D? And then also there's a prediction axis in time. Can you predict, for the car, the pedestrian could be 2 seconds, 3 seconds in the future.
Yeah.
Have you guys thought about kind of those two?
We have. So the 4D SAL is actually going to be 4D and object completion. So this is like how we envision the actual final work. For prediction, there have been a lot of forecasting methods, LiDAR forecasting. So adding semantics into the mix is pretty trivial, right? And then you do improve forecasting if you know the semantic class of the object. Yeah.
I'm going to say one more question.
Yeah.
So for the pseudo modeling produced, I think that if something is on the road, it means that it can be highly damaged or really likely that the geometry is somewhat modified. Comparing with the normal state, then I'm not sure that model can actually model it correctly. So is there some kind of principle that make it?
So this is a very good question, actually, and we should find some data for that. I haven't tried, but the thing is that, as I said, the semantic part of SAL is not really on par with what we would like to see, right? So how I would suggest to use SAL would be to do retrieval on the image space, where you actually also use appearance, right? And then do localization with SAL, right? Because in the end, SAL can be promptable, like SAM, right? You can train it to be promptable, spatially or, however you want. And then the thing that SAL would give you is the localization in 3D of that object. And in that sense, I think this could work. If it's just pure SAL, I agree. I don't think this is going to work if the shape is completely different. Yeah.
With that, I would like us all to thank Laura very much.